might help us explain something in electronics. So it always helps to form analogies. And this is a very simple stuff. I'm sure you have seen it. So the wavelength of light we know is equal to speed of light divided by the frequency. It is also can be written as Planck's constant divided by the momentum of photon. It turns out that same thing is true for electrons. So electrons we know are particles, but they behave like waves, right? Can you give me some example where electrons behave like waves? Where is it that you might have seen behavior of electrons like in electron microscope, right? And microscopy works with waves, okay? And the only reason, as Babita was saying yesterday, you can see much smaller things with electron microscope is because the wavelength of electron is much smaller. Okay? So if you really think about in physics, if you're talking about very small particles, it's hard to say if something is a particle or a wave. Okay? Same thing will have both in nature. Like photons are particles, but light also has a wave. Same thing with electrons. They are particles, but they have a wave. And you can see that the relationship is similar. And this I'll skip because even at a deeper level you see similarities. And again, I'll skip that. So you have a photon wave, light wave, electron wave. There are similarities, and this we can see. So I want to see some similarities between photons and electrons. Okay, and I don't know if you have read a little bit about optical fibers. So what an optical fiber is that you have a medium of high refractive index and surrounded by the low refractive index on either side. Okay? So if you have light propagating in the core of an optical fiber, it basically reflects like this. Okay? If you have a ray of light, it reflects. It does not go on the lower refractive index side. And if you analyze this in terms of a wave, then you will see that the electric field actually looks like this. Okay? And this is one mode of an optical fiber. Okay? And although we say that light does not go on the smaller refractive index side, but there is always a plane of light actually going. If you analyze it more carefully, okay. So this is something like tunneling. Okay, I mean light is trying to go on the other side. Okay, although classically it is not allowed. Okay? Now something similar is seen with electrons also. If I have an electron in a potential well, okay. So here I have an electron which has some kinetic energy, but it does not. It's like an electron is in a hole. It does not have enough kinetic energy to go out. Okay, so it is trapped in this potential. Okay, and this is one problem that with quantum mechanics you probably have worked out particle in a box. Okay, and what you will find is that if this potential well is not too deep, although classically it is forbidden, but the wave function of the electron will still go out on the other side. So it's again something like that. And I only just want to say that you can see the similarity between light and electron. Okay, there are other areas of similarity as well. So, like people that make waveguides, like you can have planar waveguides. Once again, similar to what I said before. You have high refractive index, medium, low refractive index, medium on either side. And so light, of course, bounces back and forth like this. It does not go on the low refractive index side. And so you have 1D confinement of light. This is called planar waveguide. The confinement is only in this direction. Okay, so it's a 1D confinement. Similar thing we can have for electrons. We can have 1D confinement of electrons, like in a thin film, okay, of a semiconductor, and that is called quantum well. So it has some very interesting properties that we touch upon. Then of course you can have 2D confinement. So you have nanoscale confinement in one direction. Of course, you can have 2D nanoscale confinement in two directions. So we have the classical optical analogy is optical fiber. So light travels only in this direction, but it's confined in x and y direction. So it's 2D confinement. The similar thing we have for electrons also. You can have what is called quantum wire. You have nanoscale confinement in two directions. Okay. And then finally, just like you can have a microsphere in optics, you have 3D confinement. So you can have 3D confinement for electrons also, and nanoscale confinement, and that's called quantum dot. And these things are very interesting properties that we talk about. Okay, obviously not everything is the same between the light and electrons. There are similarities, but there are obvious differences. And wavelength of light, of course, we know is of the order of a micron, whereas electrons have a wavelength of the order of a nanometer. And then, of course, there are other differences as well, like light has described by vector field, electric and magnetic field, whereas electrons, of course, are described by wave function, and then some other differences as well. So obviously, what I'm trying to say is there are lots of similarities which will help us understand, phenomena in nanophotonics, but there are obvious differences. Okay, again, this is one slide I want to touch upon. So here, what I'm showing you is a crystal, electronic crystal. It could be a crystal of sodium chloride. It could be any other crystal, PGS, whatever Dr. Agarwal talked about that yesterday. And typically, a crystal, of course, is a periodic array of atoms or molecules, right? And the spacing of these atoms in a crystal is typically about a nanometer, a fraction of a nanometer. Okay? So this is an electronic crystal. And if you look at the energy levels of electrons in a crystal, then what you will find is that the energy levels actually bunch as a valence band. Then you have lots of energy levels of electrons, valence band. And then you have other energy levels in this conduction band. Okay? And it so turns out that there is a region of energy which is not allowed, which is for electrons. And of course, the reason why it happens is because for electrons with this energy, if you shine that electron beam, it just gets diffracted out. So that is not allowed inside the crystal. Okay? So that's I don't know, again, if you have taken a course in semiconductor physics or even basic solid state physics, but this is a very, very characteristic feature of a crystal, electronic crystal, that you have valence band. Here the electrons are tightly bound, they are not free to move. Okay? And in conduction band, the electrons are free to move. So anytime you want to have free electrons moving in a crystal, you must somehow excite the electrons from valence band to conduction band. And that's what happens in a solar cell, for example. When you shine light, the electrons get excited, okay? Or even detectors, that some people were talking about yesterday. I mean, if you want to detect light, then of course, light must have a wavelength. Light must have an energy greater than the band gap. So the electrons will be excited from here to here. And then, of course, if you apply a battery, then the electrons will be connected by the battery. And so that's something I want you to keep in mind, that electrons are tightly bound here, they're relatively free to move. But we'll come back to this. Now, since we are comparing light and photonics and electronics, you can, just like an electronic crystal, you can actually artificially build a photonic crystal. Okay? And of course, electrons have a wavelength of the order of nanometer. So this periodicity is of the order of a nanometer. But wavelength of light is hundreds of nanometers. And so we want to make this structure where the periodicity is hundreds of nanometers. Okay, so this can be done artificially and by lithography or some other technique. So if you can have a periodic array of changing refractive index, okay, but the period is about a few hundred nanometers, then you can generate photonic crystal. And it so turns out that just like you have a band gap for electronic crystals, you have similarly a band gap for photonic crystals also. And again, I want you to keep in mind, so what this means is that if I shine light, which has a frequency here, then that cannot propagate inside this photonic crystal. It will be thrown out, okay? Just like the electrons are thrown out. The electrons cannot have this energy. Okay? And really what happens is that that light is diffracted out by this photonic crystal. Maybe I can skip this just in the interest of time. Okay, so maybe I'll just touch a little bit more about this nanoscale confinement of light and near field microscopy for sub-wavelength resolution. And yesterday, I think Padmaja had mentioned that there's a limit to how much you can resolve with ordinary microscopes. That is far field microscopy. That is far field microscopy. Okay? The traditional microscopy that you do in any laboratory that we have in our own laboratory, you must have seen in any undergraduate lab, that works with far field microscopy, because the reason is that the spacing or the distance between the object that you are trying to see and the objective is typically a few millimeters, so that's a very large distance. And with the far field microscopy, the formula for how much you can resolve is given by this. Okay? This NA is a numerical aperture of the order of 1, lambda is the wavelength of light. So you can see that the resolution is of the order of the wavelength of light. Okay? You cannot see much smaller than 200 nanometers. But this can be overcome. Let's read this. This can be overcome with near field techniques by having nanoscale apertures, or by using apertureless techniques which enhance light interaction with nanoscale dimensions, the nanoscale tips. And this idea was actually first proposed by somebody called Sinch in a letter to Einstein in 1928, because people always thought that how can you use a wavelength of 500 nanometers to resolve 50 nanometers? You cannot do that. But obviously, you can, near field technique. And again, very quickly, basically what we do is you squeeze light through nanoscale apertures, and then of course, if you have an object very close to the aperture, okay, if you have an object which is just 10 nanometers away from this aperture, then this object will see near field light, okay, the light that is trying to squeeze from that aperture. So of course, you will see point by point, okay. What you have to do is you have to move this source of light, and every time you will expose a new point on your object, and then of course you see from this side. Okay? So it's a slightly different technique, but you can see an object with nanoscale resolution. And of course there are related techniques, called apertureless imaging. Here you have a metal tip, and if you just move. Just like outside this aperture, you have near field light up to say tens of nanometers. In exactly the same way, if I have a metal tip here, if I shine a laser, then close to this metal tip, you have near field light. You have near field radiation. Okay? You have some extra radiation that you don't see at long distances. And so just by moving this metal tip, you can actually see. You can make that near field light interact with particles of the object of the substrate, and you can see by that technique as well. Okay, so these are techniques of near field microscopy. Okay, this we can just spend a little time on it. Again, if you have had some mathematics, I don't want to deal too much with it, but this graph actually tells you how much is the intensity coming out from a nanoscale aperture. And you can see that the intensity is basically the diameter of the aperture, lambda is the wavelength of light. And so you can see that as this ratio A over lambda decreases, that means wavelength increases as compared to the aperture, or the size of the aperture decreases in comparison to the wavelength. The amount of radiation coming out from this aperture rapidly falls down. So this is basically the far field light that is being radiated away from the aperture. So almost nothing comes out again. But if you look very close to the aperture, and if you analyze what the electric and magnetic field looks like, then you will see that it has all these components. There are some components of electric field which fall off as 1 over r, and there are others which fall off as 1 over r squared, 1 over r cubed. And now you probably know in your undergraduate E&M that intensity of light is what square of the field, right? And so if I square these field components, you can see that some components will fall off as r raised to 6, r raised to 4 if I square it, and this will fall off as r squared, okay? So something which falls off as r squared, we know that the intensity goes as 1 over r squared in a real radiating light. So this is the far field component, which is the usual thing. But there are these near field components as well that you will not see even if you are few wavelengths away from the aperture, you will not see the near field components. You have to be very, very close to the aperture